Multiply by the conjugate.
Right, we should do that step where we multiply by the conjugate. So it's the conjugate of the square root thing. It could be in the numerator or the denominator. It doesn't matter. You multiply by the conjugate of that square root thing, which is the square root of x plus 3 plus 4. And you multiply by the square root of x plus 3 plus 4. That's the game. It cleans it. It fixes it up. It's beautiful. In the numerator, you should FOIL it out. FOILing it out will give you the square root of x plus 3 times the square root of x plus 3, which is x plus 3. The middle terms cancel, so the next thing you get is this minus 16. That's what you get in the numerator. When you FOIL it all out, the middle terms cancel. You get the first and the last like that. The denominator, please do not FOIL out. The denominator, leave just like it is. I mean, it's multiplied together, but don't FOIL it out. This is awesome. What is this? This is 3 minus 16. This is x minus 13. The x minus 13 can cancel with the 13 minus x.
Right.
But when you cancel it, it leaves you a negative 1.
Why is it negative?
Well,
Not a one.
hang on. When you cancel an x minus 5 with an x minus 5, what are you left with?
1.
1.
Right.
Right. You're canceling something with itself, you're left with 1.
Right.
When I cancel a 5 minus x with an x minus 5, they're not the same thing. They're off by a negative sign. One's the negative of the other one.
Gotcha.
You could factor out a negative sign and see that. If you factored out a negative sign, he would be a negative 5 plus x. And now he's the same thing as the denominator. Anyway, I just like to say cancel them and the answer's negative 1. If you believe that they're off by a negative sign. They're negatives of each other. You cancel them and leave yourself a negative sign. So cool. So I'm saying these guys cancel. I'm left with negative 1 over this. And don't forget, see, I get a little sloppy, and I know you guys get a little sloppy. The proper notation is there's a limit out in front of this problem. It should be sitting here. I mean, we should kind of have this limit every time we write a new step. This limit is here. But now is the step here where I'm finally ready to do the limit right now, which means plug in the 13, and you'll get an answer. You'll get negative 1/8, I guess, won't you? Plug in a 13, that's a 4 plus 4. What about continuity questions? Or hang on, one more thing before continuity. We should do some continuity questions, but what about these 2.5 questions? I've done here. I'm making one up here. I'm making one up. Dude, this is a beautiful problem. I make up good problems. And then I'm the guy who makes up your tests. So anyway, this is a good problem. Step 1 of doing limits, plug it in. Plug it in. By the way, at first glance, you see this square root crap, and you might think, oh, it's one of these conjugate deals. You know, it may not be. What led me to do this conjugate? I had that 0 over 0. Remember, if you have 0 over 0, you need to fix it. The conjugate helps me fix it. This one's different, I think. Even though I put a square root in it, when you plug your 7 in, oh, by the way, it's 7 from the right, but at first that doesn't even matter. You still just plug the 7 in and see what you get. It is 7 from the right, but at first you just plug a 7 in. What do you get? You get 9, square root of 9 is 3. 3 minus 1 is 2 over 0. Now 2 over 0 is not, that's a special thing, man. That's what we learned about in 2.5. We learned that a number over 0 is not some weird indeterminate thing. A number over 0, in terms of limits, a number over 0 is infinity. It's infinity. It's infinity. Now, it's either positive infinity or negative infinity, and that's the part I got to figure out. Let me think. How do I figure that out? Because I'm coming to 7 from the right, I'm on this side of 7. I'm at 7.01. So when you subtract a 7 minus a 7.01, this 0, which is not really a 0, but a teeny-weeny number, is it a teeny-weeny positive number or a teeny-weeny negative number?
Negative.
I think that's negative, don't you? So it's a teeny-weeny negative number divided into a 2. It's negative infinity. I'm done. Those were cool. I mean, those were good, man, but you have to think like I've tried to teach you to think.
So you took 7 minus 7.01, and then...
Because it was coming to 7 from the right, I was analyzing this 0 in a little more detail. Right, exactly. I think of this 0 as a teeny little number. I don't think of it as a 0. In terms of limits. Because x is approaching 7, it's never really getting there. This is never really a 0, okay? We throw it in there quickly and we say 0. But we're doing a limit, and it's never really quite a 0. So it's a teeny-weeny number, and I just got to figure out, is the teeny-weeny positive number or negative number? And that'll help me decide whether it's negative or positive infinity.
And so once you subtract that, you get a negative 0.
I mean, don't you get a negative? It's negative. Right, right.
So the way you would write your answer is?
Just like this. I mean, I'm showing my work. There's not much work to show. I mean, right? Look, I mean, my work is when I see a number over 0, I'm thinking infinity. I just had to do this teeny little bit of work here just to kind of figure out. Yeah. Now, I just made that one up, and that was that easy. There's others. There are others. Let's see. Like number 6 is kind of like that. What do you want to say? Number 2 is like that. Number 6 and 2 are both are good questions. Go ahead.
Looking at number 18, I just had a question.
Okay. I know. Hang on. We're good. Anything else on this? You want me to do another one of these? I mean, I don't know how crazy can I make it. I can't make it.
Do one coming from the left.
Well, see that? Sure. Or really, what I like, yeah. See, here's one we could argue about. You ready for this? All right, this is beautiful. You ready? Let's argue about this.
It's from both sides.
Good. There is no left and right. It's from both sides. Anyway, step 1. Plug it in. All right, you plug it in, what do you get? 24 over 0. All right. What's a number over 0?
Infinity.
Infinity, man, I swear. It is. Yes. It isn't. It's infinity, because you got to look at it as, look at that 0 as a teeny-weeny number, and then it makes sense. Because how many times does this teeny-weeny number divide into 24? Thousands, millions, billions. How many times does a little 0.001 divide into 24? Millions. It's infinity. So it's infinity, but maybe it's positive, maybe it's negative. Now I gotta get real close to 2 and figure this out. In fact, what I usually do in a problem like this is now, because it's not the left or the right, I go investigate both options. I need to go investigate the limit as you approach 2 from the left and the limit as you approach 2 from the right. Now here we go. Watch what happens. You ready? If you approach 2 from the left, listen, it's still a 2. You plug it in, you still get 24 over 0. You still get 24 over 0. But hang on, we got to figure out if this is a positive or negative 0. It's all about that 0 being positive or negative. So hang on, it's from the left, so it's like a 1.99. So a 1.99 minus 2 would be negative, but the fact that you're squaring it makes it positive. So that squaring kind of threw a kink into this problem. This dude is a little positive answer. The numerator's clearly positive. What can you say now about this answer? Positive infinity. From the right, you're at 2.01. When you plug in a 2.01 and subtract 2, you're a teeny little positive number. You square it, you're still a teeny little positive number. And basically, you got the same thing, 24 over 0, and it's positive. So what's that answer? So we got an answer from the left and an answer from the right that are both positive infinity. What do you go say about this answer? I would say that.
So its graph looks like that.
So they're both going.
What's it look like?
Its graph looks like it's got an asymptote at 2. And when you approach it from the right or from the left, they're both going to positive infinity.
There you go.
That's what he is, turns out. His graph, looking at his graph would help. I'm trying to do these analytically, I guess. I'm trying to get you to analyze the little 0. It makes sense to me. So I'm trying to get you to think about that little 0 being positive or negative. Now, what if he would have been positive and he would have been negative? Then what do I say about this?
Does not exist.
Right. When the left and the right aren't the same, I say does not exist. But if they're both headed to positive infinity, I call the answer positive infinity. And listen, that's where me and the book might argue. If you're reading the book a little or trying to, me and the book might argue about that. They kind of like to say if you're going to infinity, it doesn't exist either, man.
Right.
I mean,
Yeah.
and I get their point, but I like to know where the hell I'm going. So I want to know if it's, you see what I'm saying? You've heard me before. I've sort of reserved does not exist for when the left and the right don't match. That's kind of what I've reserved that for. Or when you have 2 different answers, then you say the answer does not exist. So when you have one answer, even if it's infinity, I like to know that the answer is infinity. Anyway, that's a little 2-5. I think we should work on those continuity questions maybe on the back. She was asking me sort of about 18. Did you want me to elaborate on 18?
Yeah, I mean, if you could do it, then I have a question.
So 18's kind of nice. It's not piecewise, and so it's one of these where I just give you this function. It's x minus 3 squared over x squared minus 9. You know, so the question is, where is it? Is it discontinuous anywhere? And if it is discontinuous, you tell me where, and you tell me if it's removable or not removable. So, but in a question like this, we've kind of learned that the game is factor and see which factors cancel. So in the denominator, it's the difference of 2 squares, which factors like this. The numerator, that's the denominator. We should all know that, I suppose. And then the numerator is just actually already factored. I'm going to write it like this, but that's what x minus 3 squared is. And then you can sort of see that this one cancels away. But that doesn't mean in the original problem he's still there, actually. So, all right, hold on, stop. So where is it undefined? This function is undefined and therefore discontinuous. This function is undefined and therefore discontinuous at
X minus 3.
Well, both these places, at x equals 3 and at x equals -3. But, so I didn't mean to cancel too early. I'm sorry about that. I meant to say, let's stop and see where he's undefined. He's undefined at both those places. The one that cancels out is still called the discontinuity, but now he's called removable. He's a hole, is what he is. And the one that doesn't cancel out is a vertical asymptote, and we call that non-removable. So when you're presented with a function like this, with asymptotes and holes, this is the approach. When you're presented with a piecewise function, we got a different approach, don't we? I mean, that's when we go through our three-step definition, and it's a different approach. But when you're presented like this is your approach. You just need to find all the places where it's undefined. Those are going to be discontinuities. But if you happen to cancel one away, they're called removable. Those aren't. Those are non-removable.
Is it always going to be that if you can cancel one away, that they will always be considered removable?
Yeah.
Or if they're
In that game, yeah. In that particular game, I mean, I guess
There's no
15 is similar, right? What's 15? 15 is a function x squared plus 9 over x squared minus 9. This one's funny because the numerator doesn't factor. The sum of two squares doesn't factor. The numerator doesn't factor. The denominator factors. It's of course it's x minus 3x plus 3. But since that numerator doesn't factor, nothing cancels. And so I got a couple discontinuities here, just like I did before, except this time they're both non-removable. They're both discontinuities at both those places, but they're both non-removable. For number 15. They're asymptotes. Yes, ma'am?
You don't have to check the limits, right?
I
See, that's what I was doing.
I mean-
Still got the same answers.
Right. I just know, I guess I've sort of shortcutted.
Okay.
If you can cancel away one of those factors in the denominator, then it's called removable. If you can't, they're called non-removable. So, I've kind of shortcutted my way
See
through that
because
definition.
I think
Right.
before we had to do all that.
Right.
Okay. That's good.
Yes, sir.
I have a question on 7 on the quiz, and I would like to find out
Yes.
why is number 5 discontinuous removable?
I'll help you with that.
That's why I got
So he's asking about his quiz, our in-class quiz the other day, and he's asking about 7, which was kind of a cool function. It was a piecewise function.
right.
It was 4x squared plus 2 when x is less than 5. It was 102 when x is greater than 5 but less than or equal to 9. And then it was something else, x squared plus 5x minus 14 when x is greater than 9. All right, you ready? By the way, what's the question?
Determine whether the function below has any points of discontinuity. If so, list them and classify them as removable or non-removable.
Right.
If not, right.
Right. So find all the discontinuities and list them as removable or not. Right. That's the directions. Removable or not removable. Well, so who are you looking for? I mean, before 5. Again, I like to say this. Before 5, on the left of 5, is there any discontinuities to worry about? No. Between 5 and 9, is there any discontinuities to worry about? No. Greater than 9, is there any places we need to worry about? Holes or asymptotes or any? No. Right? Right. There's none. How do you know that? Because you got nice polynomial parabolas and nice stuff here. You got no crazy denominators or anything. So I'm not worried about any of those places. So what am I worried about? I'm worried about at 5 and at 9. So let's go investigate what happens at x equals 5. And if I use my 3-step definition, it helps. I think it helps. Here I go. Step 1, is what's f of 5? So then I got to figure out when x is 5,
Right.
how do I plug it into the function? And I look up here, and x never is 5. Nobody ever put an equal to on this. I mean, when it's less than 5, I work with that. When it's greater than 5, I work with that. What about when it's equal to 5? I don't know. It ain't listed. In fact, what it is it's undefined. I mean, was that subtle or what? It was about this. Hey, it was this. If there was an equal to sign there, then you would have plugged 5 into the top and got an answer. But it was about there ain't no equal. There's no place for me to plug 5. It's not defined. So right off the bat, you failed. I mean, you failed. It failed. It's a discontinuity. It failed the test. It's a discontinuity. I wonder if it's removable or not. To investigate whether it's removable or not, I think I'll go ahead and investigate step 2, because I remembered that when the limit exists, those are removable. When the limit doesn't exist, those are non-removable. So I need to, even though I know it's a discontinuity and it already failed step 1, I still need to investigate step 2. I want to see if this limit exists, just to help me classify it as removable or not. Are you with me? So here we go. Now I'm doing the limit as x approaches 5. Well, of course, I'm going to do the left and the right, because this is a piecewise function. And so on the left of 5, you plug in a 5 there, and you do the work, and what do you get? 102. Do you agree? And on the right of 5, you're over here, and you would plug a 5 in there. Of course, there's kind of nowhere to plug it. You get 102. And therefore, this limit is 102, and this limit exists. But we already know he failed step 1, so this guy is a discontinuity point at x equals 5, and he is now considered removable since we found out his limit exists. See, you know, as I'm doing these problems, I know they're written out analytically and they're step by step, but I do have pictures in my head. I mean, when I do this limit from the left is 102 and the limit from the right is 102, in my brain I'm seeing this stuff matching up. I mean, the left and the right limit are matching up at 102, but if we look up here, it was undefined, so there's sort of a hole there. I mean, that's kind of the picture of what's going on. Oh, well, hang on. All right, hang on. Yeah, hang on. You might be on with something. Anyway, on your quiz last week, this was question 7, and tons of people kind of screwed this part up. What did they do? Oh, they kind of lost this. They kind of didn't catch this idea, and they kind of went with this idea, and they kind of assumed that it was continuous at 5. They kind of ignored the fact that there is no function value, therefore it's discontinuous. So a lot of people wrote that it was continuous at 5 because the left and right matched up. But the subtle thing was there wasn't any function value, so it was discontinuous. If you do the 9, if you go investigate the x equals 9, like we should, let's see what happens. What's f of 9?
102.
Because you plug it in there where the equal to is, and you get 102. All right, that's step 1. Cool, it has a value. All right, what's the limit as x approaches 9? Well, I got to do the left, and I got to do the right. Let's see, when I'm on the left of 9, where am I? On the left of 9, I'm 102. And then when I'm on the right of 9, I would plug a 9 in here. And be careful, but I think the answer is 112. And so it's not 102. So this limit does not exist. And therefore, once the limit doesn't exist, he's a discontinuity. And what kind of discontinuity? Non-removable, because the limit does not exist.
Wasn't it there at first step?
What did you say?
Wasn't it there at first step? What do you have to check? Wasn't it 3 steps?
Yeah, you just do
Well, but I already failed. You're right.
FC does not.
I failed step 2, so I'm done. What is step 3? Step 3 is, if this has an answer, and we do get an answer here, but see, we didn't get an answer here. But if we did get an answer here, step 3 says this answer better match this answer.
To be continuous.
The limit has to be the function. That's step 3. Number 12 is a true or false question on your practice thing. And it says, if f is undefined at x equals c, then the limit as x approaches c does not exist. If it's undefined, does that mean the limit doesn't exist? Not necessarily. And a good picture of that is this. Here's a function, here's a thing. Here's a place where the function is undefined, but the limit clearly exists, doesn't it? The limit exists here. The function's undefined, there's a hole, but the limit exists. What if we do number 20? Let's try 20.
Yeah, I had, did you notice the water maker from Citrus?
Yes.
He and I worked this one out yesterday.
Good. He knows what he's doing, I suppose, doesn't he?
Yeah, he's kinda awesome.
Good. Sine of 2x over x. X is greater than 0. And x is less than or equal to 0. So this is number 20 on the practice. Let's see. We're investigating continuity. You know, when we investigate this continuity, we're always doing it at a point. So which point should I investigate?
0.
Yeah, thank you. And that's right. Good job. That's who we're investigating. Now hang on, let me just think for a second. When we're less than 0, are there any other points I should investigate less than 0 where this might have problems? The answer is no. This is a beautiful continuous function. There's no undefined places or anything on this guy. So, and what about greater than 0? Is there anything to worry about when you're greater than 0?
No.
No, I can sort of see the only real place to worry about is 0. Right. So I'm worried about 0. So I'm going to do my 3-step definition at x equals 0. What's the first step? Plug it in and see if you get an answer. So when you do plug in 0, what do you get? First of all, when you plug in 0, you pay attention to the equal sign and you plug it in up here. And it's not hard. You plug in, you get e to the 0. That's 1 times 3. It's 3 minus 1, so that's a 2. So we get 2. All right, cool. So we're past step 1. Let's do step 2. We need to do the limit. Well, I'm doing the limit as x approaches 0. Okay, well, that means I got 2 limits to do on the piecewise function. What I really got to do is these 2 limits as x approaches 0 from the left and as x approaches 0 from the right of this function. All right, here we go. Let's see, from the left, from the left, from the left. From the left, you're up here, and basically you plug in a 0 and you get 2. All right, that's awesome. From the right, you're here and you plug in a 0 and you get that 0 over 0 thing. This looks a lot like my famous theorem. It's only my famous theorem if this can match this. How do I make this match this? Multiply by a 2 in the denominator. Force that to be a 2x. Well, if you multiply by 2 in the denominator, you have to multiply by 2 in the numerator. So I'm putting a 2 here. I'm putting a 2 here. That is the theorem which says it's 1. 1 times 2 is 2. Even though I was from the right, I was sort of ignoring. Anyway, the from the right meant I was working here. And anyway, I get a 2. Are you guys all right? So step 3. So what's the answer to this limit? 2. Well, thank you, 2. And then what is then, step 3 says, this better equal this. Well, god dang it, it does. 2 equals 2. Wait a minute, does 2 equal 2? Wait a minute. Does 2 really equal?
Only on certain days.
I'm sorry. On Tuesday, yeah. 2 equals 2. We're cool. We passed the test. This guy is continuous. You know, all you really proved is it's continuous at this point. But the truth is, there was no other points to investigate, so we know it's continuous everywhere, really. But what we just proved here is that it's continuous at x equals 0, and there are no other discontinuities. Right. All right, you guys want to quit? We can go overtime.
I just have it. Sorry.
All right, that's okay. All right, we'll quit. You can leave. But if you've got another question, I'll address it. I'll hit pause here.